The goal of this video is to explain how to use the solver add-in in Excel to fit a curve. So give me just a second and we'll get right into it. Again, the goal is to fit a curve with the solver add-in in Excel. So let's start with a screen share. And let me explain a little bit about this spreadsheet. Suppose I was doing an experiment and I was trying to analyze a magnetic field versus position. So I just put a sensor out and measure the magnetic field at various points in space. And I record errors associated with that while I'm taking those measurements. Cool. Who cares where those come from right now? Suppose your instructor says, well, it's probably one of these two theories. Let's see which one fits the data better. That seems like a reasonable question. We see two different theoretical formulas, and we're trying to figure out which one should fit the data better. So in order to use these formulas, maybe looking at the constants really quick, B stands for magnetic field. So B1 is a constant value, which represents the magnetic field strength when X equals 0. X is the horizontal position left and right. L is something that determines the spatial dependence. Similarly over here, B2 would be a constant for the magnetic field strength at position X equals 0. And K is something that describes the spatial dependence. So what I'm going to do first is I need to come up with some numbers for these if I'm going to generate theoretical formulas. So let's just go into here and look. This is pretty close to 0. So I'm just going to say whatever value we have there, it looks like about 128. So I'm going to type in 128 for each of those. That seems like a reasonable theoretical estimate. It's the largest field there at 0. And then this length, I'm just going to put in the number 1 for right now because I have no clue. Now what I'm going to do is I'm going to use the red theoretical formula or B1's theoretical formula to compute this. So I've already typed in some constants, so let's just get to it. Equals B1 basically divided by 1 plus A10. Oh, I better put parentheses around that. A10 divided by L quantity squared. And put parentheses around that. So again, B1, that's just the constant parameter up there. And then this is that basement. Okay, 1 plus X is A10 over L quantity squared. So I'm going to hit that. Residual, that's just the difference between the experimental value and the theoretical value. So I'm just going to type that in for residual 1. That's the experiment minus the first theory. And then for residual squared, that's just equal to the residual squared. More on that in a minute. Now let's get to theory 2. We're using the second theoretical formula, the blue one, B2. So that should equal B2 times EXP, means e to the, let's see, negative K times A10 is X, and then I'm going to square that. So that gives me that theoretical formula. Again, B2 is the constant value that we expect at the origin, K is the constant parameter, and A10 is X. So I hit that. And then the residual for number 2 should be the experiment minus the theory for number 2, and the residual squared should equal that cell squared. All right, so now I can just fill all these down at once. There we go. Great. Now, I'm going to do, even though you might not know why, I'll explain why in just a second. I'm going to do the sum of the squared. So I'm just going to add up the squared residuals. So sometimes I've seen that SSR. Right? I'm going to do the same thing here. I'm adding up the sum of the squared residuals. Now, before we get too far along, we should make a plot of this. And I actually did that. So if you're not sure, you could highlight the X values, then highlight the Y values like this, and like this. So obviously I highlight the X values first, then press and hold Control, then highlight the other columns. And I did that. I inserted a graph, and I've actually formatted one here. So I want to just use the one that I've already formatted. So sorry if that's confusing. I can give you other videos on how to make the graphs later. All right, so now you can see we've got these graphs. So the first thing that I'm going to do is mess around with these parameters to see if I can make the fit look somewhat reasonable. So again, the dots here with the error bars, I got those from right here. Those are the experimental values. The red solid line curve is the red theory, theory 1, and the blue dotted line curve is the theoretical curve number 2. So let's just play around with this. If I make this bigger, that's starting to look pretty good. Maybe 5, I don't know. That's starting to look pretty good. And then maybe K. And now maybe while I do this, watch the sum of squared residuals. Watch the number here for the sum of squared residuals for the blue curve. I'm going to change this number to say, whoops. I'm going to change this to 2 and see, ooh, that gets worse. Look at the sum of squared residuals. It gets larger. Let's try going the other way. If I take this to 0.5, it goes from 82,000 down to about 62,000. It's looking better. How about 0.1? It's getting down much lower. And so we see that the better the fit of the curve is, the smaller this sum of squared residuals is. If you're wondering what the sum of squared residuals represents, let's just take this blue curve. The distance between a single data point and the predicted or theoretical curve is the residual. So we can see that there's a bunch of different residuals here. And so all of these blue lines that I'm drawing represent the residual for each different point. And then what we do is some are positive and some are negative. That's why we square it before we minimize it. Okay, so if we square it, then we don't accidentally get a fortunate coincidence that gives us a bad curve fit. All right, so let me clear those out. So that's what the residuals mean, and that's why we're doing this. So let's keep going. Let me get a little bit better. Whoops. Let's go to 0.05. That's starting to look pretty good, maybe even 0.04. All right, so what I did there is I basically eyeballed it. And this is a great start, but this is going to take all day if we're trying to minimize these. So what we want to do is use this thing called the solver. So, and let me just do this just because I know sometimes I'm going to just give me a second here. So in this case, the solver right here, you may not see this on the data tab on yours. So one thing you might need to do is go File. Whoops, sorry. Home. Let me see. Let's do this again. Oh my gosh. File, Options. That's right. Sorry, I'm spacing out there. After you do Options, you click Add-ins. And then for me, I went down here to the Manage Excel Add-ins Go. So I'm looking right here. All right. And when I do that, I click Go. And so you may need to click this button here for the solver add-in and click OK. And this is a free add-in. So now once I do that, hopefully the solver shows up on the data tab. So if I click these various tabs at the top on the data tab, you should see the solver. So now let's get into this here. And maybe just so you can see all this, I'm going to, oh my gosh, let me do something really quick here. There we go. That way we could see it all on the screen. Apologize if the font is a little small. So what I want to do is minimize the sum of squared residuals for the red theory. So I'm going to click the solver and I need to tell it which cell. So I'm going to click this button here, or I could type it in. I'm going to minimize that cell. And then I want to use these two parameters. I'm going to adjust the constants. That's what I'm going to adjust in my fit. And now I'm just going to click Solve. And when I do this, watch the numbers for B1 and L. Let's click Solve. And notice they change. And I'm going to click OK. And notice the sum of squared residuals is lower than before. So it did a small algorithm to minimize the sum of squared residuals and outputted these two values. So that's what the best fit is in terms of minimizing those. Let's do it again for this one. Let's use the solver again. And again, this time, I'm going to fix this one. And here, I need to use these sets of parameters. So when I do that, I'll click Solve. And again, we see a different set of parameters show up. And notice this interesting fact here. Notice the sum of squared residuals for theory number 1 seems to be slightly smaller than the sum of squared residuals for number 2. The error analysis of these might be pretty complicated, but this does at least give us some indication that both of these models seems to be approximately the same. Maybe theory 1 fits it slightly better. Okay, so that's the basics of this. Now, regarding this, I actually took this a step further. And so let's see, what are those numbers? We got 121 and 6.19 and 119 and 0.020. In a lot of experiments, I'm going to go ahead and save that really quick. Just get rid of that, and I'll bring up another one. So here is another version that I did where I said, well, what happens if there's an offset? So let's look here. So this would be a vertical offset, right? That would be this term right here, this vertical offset. This would correspond to, what if my sensor had a small zero correction that I forgot to zero off? You might think, oh, this could improve the quality of my fit. Okay, and what about this right here? So basically, this is a horizontal offset. Anywhere you see X, you replace it with the X minus X horizontal offset. So that's what this term is. And I did similar things here. I did a horizontal offset for the blue theory, and I did a vertical offset for the blue theory as well, or B2. So what I'm curious about is, will this make the fit better? Now, in general, as you add more fit parameters, it should become easier and easier to fit the data, and we should be able to get lower values. So just popping these numbers in, the fit from before was, I think it was 121 and 6.19. That was the fit from before. And for B2, we said it was 119 and 0.02. All right. And just to show you that these offsets work, I'll put in an offset of 10, and we see that shifts it up. Let's put that back. And if I put in an offset of 2, you can see that shifts it to the side. So that's what those offsets are doing. And again, I'll do the same thing here just to confirm that I punched in those formulas correctly. And then here, let's do an offset of 2. So you can see that those actually do offset them, and I entered the formulas right. Whoops. Let's type in 0 for those and get them all back. So we're going to start assuming there was no offset. If you're curious, there's the formula for the horizontal offset and vertical offset for the red theory. When I typed it in, there it is for the blue one. So you've got that. Great. So now let's see if we can lower these residuals. So notice for the red, it's 515. And for the blue, it's 595 or so. So when I do this, let's go in there and minimize these with the solver. So I'm going to go to the solver. I'm going to do this one. And I believe I've got it all in there correctly. E21, yes. Okay, we're good to go. Notice I was able to lower it, and we'll evaluate what this means in a second. Let's do the same thing for this one. This one, I need to do this cell. I want to minimize those residuals, and I need to use these parameters. Highlight those, press and hold Control, highlight those. All right, so let's do that. And notice that lowers as well. And notice this curve, boy, both those curves are pretty much perfectly lined up. But this turns out to be very unreasonable. This is something that is not obvious when you first see it. This looks like it fits much better, but usually your vertical offset is not larger than the measurement values, right? So our sensor was probably not off by 66 millitesla when we did these measurements. The horizontal offset seems very reasonable, right? So, and again, here, it seems pretty unreasonable to expect a vertical offset of 35 millitesla when we're measuring to 3 decimal places. So we're measuring in the ones column in terms of millitesla. That would be a large vertical offset to have not noticed. So I argue, even though the sum of squared residuals down here is actually lower than the previous case, this seems a bit absurd. So one thing you could do is, if you're in the solver, so if we go into here, whoops, let me click a cell and click solver first. One thing you could do is you could add some constraints. So maybe you want to take this vertical offset and maybe you think it should be less than or equal to, a few. So maybe 2 or 3 or something, right? And so we could try and see what this does. And notice we get back almost exactly the equation as before. Now, so it's probably in this case unreasonable to add in this fit parameter, and it seems like these offset parameters were not significant. So this is something that you probably need to handle on a case by case basis, whether or not is it appropriate to add offsets to your fit parameters. All right, and one last thing that I thought I might mention here, I did something similar with a linear fit. So let me see if I can get back that other one again. Hold on a second. Sorry, this is taking such a long video. I think it was this one. So actually, I did a linear example here too. And I just wanted to point out that using the solver for a linear fit is probably not a great idea. So one, it's a lot more work than just doing a trend line. If I wanted to do a trend line, that's discussed in another video. But and if you do, I did the same process with these solvers, and notice uh, I get a line that is not actually fit very well. So the actual trend line from Excel is this lower curve that's pretty much right in the middle of all the data. Whereas when I use the solver and minimize the residuals, I got this unusual curve that goes through this upper bound. And so yeah, the solver may not always be the be all end all of everything, but it's a way to get started fitting a curve. And the error analysis associated with the fit parameters turns out to be a bit complex. So that would be the subject of probably a whole